Well, it's a great pleasure to be here, and I'd like to thank the organizers for giving me this opportunity to talk to you. So let me get right into it. So let's say that the characteristics of our conscious experience have spatial extension, temporal duration, and what I will refer to as a binding with the now. Now, you may not agree with that, but if you don't agree with all that, then let's just take a conscious experience which has those properties. Now, this binding with the now, so I see this as crucial to the world, that there is choice, that there is quantum uncertainty. So this is an important point I'd like to make, that and so this is likely to be controversial, that in a deterministic world, that would be a dead world. Nothing would happen. We somehow have this experience of the now, the present, and that, without understanding it, this seems to be intimately related to quantum. So what I want to do in this talk is construct a model. So I want to throw everything away. And I want to start with a model universe that will involve states of perception. So the first of these points, spatial extension, I think I can deal with. And this again is important. If my model should fail, it should at least succeed in isolating the problems in respect, and you will see that I will get into difficulty when I come to talk of time, and certainly when I come to talk of consciousness. But at least the model, I hope, might help isolate where the problems lie. So the key steps in my argument will be as follows. The world is relational, and a convenient way to represent such a world is with combinatorial structure. That is, for example, a combinatorial graph. Change occurs, something happens, systems change. And if you think of some complex system like our human body when we're sleeping, although it's not quite true, there are external influences coming in, gravity and so on, touch affecting our body, but one could maybe, in an idealized situation, think of our whole body as an incredibly complex system, and somehow it encodes the rules for its own change within it. It's this incredibly complex system. It is changing as we're sleeping. Things are happening. And somehow these changes, I would suggest, are encoded within the combinatorial structure. So that's what I'll refer to as universality. And states that derive from the combinatorial structure are implicitly present and realized and exploited to enact change. So you will see in my model that change necessarily requires states to be realized, or I'm going to, in fact, rephrase states being realized as change. I don't understand what it means to say a state is realized. The only thing I understand is that a system changes. So that is what I refer to as the manipulation of potential information and emergence. And for an essentially autonomous system, as change occurs, the conscious self emerges together with geometry and time. So I see them all interrelated, geometry, time, or the now, and consciousness. So I refer to that as higher order universality. So let me just make sure you're clear. On a combinatorial graph, there is a collection of vertices connected by edges, some of them. And the degree of a vertex, I will refer to d of x. So the degree of vertex x is 3 here, and I'll use this symbol tilde to say that x is connected to y by an edge. Okay. Now, here we see the Necker cube. So you should see a cube here, and I think of that as that is a conscious experience, in my view. you're seeing a three-dimensional cube, you're possibly seeing two cubes. And you can maybe switch between the two cubes. Okay. And I want to encapsulate that in my model, or capture that in my model. And not only that, if I change the angle of projection, this doesn't change. There are still two three-dimensional cubes there that we see as humans, and my cat wouldn't see probably if it walked across the paper there. And so where does this 3D cube come from? So I'm going to, so this is the Gestalt effect, the ability of our brain to generate whole forms. And so I want to model this in a sort of mathematical way, a standard sort of way, where we have a field and spectrum, and somehow the apparition of this cube is a realization of a state and a spectral value. And so there's a projection onto the complex plane, namely our retinae. And I'm telling you that this equation is satisfied. Let me get the equation in all its form there. So this is the equation I'm writing here. In fact, for the cube, it's very simple. Gamma is 0. Gamma x is just some real number at each vertex. There's a degree, and this is what one would think of as the Laplacian on a graph. And this is a sort of symmetric square derivative, complex symmetric square here. The sort of thing that arises in conformal in twistor, in fact, and things like that. And the fact that this equation is satisfied, just the right-hand side vanishes, is essentially Gauss's theorem of axonometry. Okay, and there are other examples. So the fact that that equation is satisfied, in fact, comes from a paper of Eastwood and Penrose, Roger Penrose, in Mathematical Intelligence in 2000. So, for example, now the equation is satisfied for the tetrahedron with gamma equals 3/4. And this gamma is, I'm thinking of as a spectral value. And again, with the tetrahedron, there are two possible states that appear. And I just slipped this slide in because I'm going to want to talk about time very shortly, or how to begin time. And one way I can linearize, so the equation 1 was a quadratic equation. And that's pretty bad from a physical point of view. One likes linear equations like the Schrödinger equation. But what a mathematician would do is linearize it. So one can linearize this equation. And then you get something, in fact, like time. When you linearize that equation, you get a time-independent part of the Schrödinger equation, sort of Laplace-type term. And then you could then try and imitate quantum mechanics by bringing in a Schrödinger equation. So you can put d phi by dt is the right-hand side. And that's a little like, so it's interesting to contemplate that in terms of optical illusions, in fact. So it's like a linear system on a background. So this isn't a precise mathematical thing, but as you introduce the background, you get the optical illusion. So one could take this path then of a Schrödinger type equation, but that's not what I'm going to do, because that would be presupposing like the Schrödinger equation was God-given, and I don't want to do that. So let me get the context a little bit more precise. So we're really talking about frameworks in Euclidean space. So that is points in Euclidean space, and they're connected by rigid bars. This is the cube. And we have an orthogonal projection, which restricts to the vertices. And we say the framework is invariant if it satisfies in my equation whatever the similitude. So that was an important point I forgot to say with the equation 1, which if I can just get it back here again. the cube will satisfy this equation whatever its position, and the same with the tetrahedron. Whatever similitude, it doesn't change the fact it satisfies the equation with the same value as gamma. And that is the important property I want to call invariance. And this means that somehow the geometry is intrinsic to the structure. You're not imposing a geometry from outside. It satisfies this equation, and the realization of the cube somehow creates its own geometry. Because whatever position, whatever similitude I take, it doesn't change the fact it satisfies this equation. And you can hope then maybe that you can, given the combinatorial structure of the graph and the spectral value gamma, which in general is a function for the regular polytope, is constant, but you might allow it to take different values on different vertices. And you might hope to be able to reconstruct the cube from the spectral value and the equation. So in fact, you can define a spectrum. You can just say that the spectrum is the set of these functions for which we get a non-constant solution. You have to identify them if both these terms are zero. Identify, so you need equivalence classes. And so you can associate to any combinatorial graph, you can associate its geometric spectrum. It's quite difficult to calculate. These are complex equations, so it's a system of complex algebraic equations, and you can go into Grosvenor bases and so on to try and calculate the spectrum and see what realizations exist. And you can sort of prove lifting theorem that if you have a solution, then you can locally lift it into three-dimensional space. And if you so this is a local lifting theorem, and if you put configured in, this means a certain symmetry assumption like the regular polytopes have. And then the lifting is unique up to two different possibilities, as you were seeing the two different cubes with the Necker cube. And so that, but if you want to have a global lifting, that's an extremely difficult mathematical problem to solve in general. But with the cube, then you need to have consistency from vertex to vertex. So you can, if you like, see the two states in this quantum mechanical notation that you have two lifts at each vertex. So there are 8 lifts of each vertices, but they have to be related. They have to, and so that you then get a state of this form to represent the two states of the cube. And there are other invariant frameworks, such as this double pyramid on a regular polytope, as the numbers of the polytope, the numbers of vertices of the regular polytope increase. There's a unique height which makes this invariant, and so in the limit it becomes a disk, in fact. And you might want to call these particles, and you might then start to want to build up your universe. Imagine a universe full of particles. And you need, at least without having brought in time yet, you need to have some sort of way that systems change. So I'm going to really skip this slide, but just to say that you can perform edge switches and preserve the solution to the equation. But to do that, you actually, so what are these edge switches doing? In fact, so it's best to illustrate this with an example. So here I've drawn it for two tetrahedra, and you do the edge switch. So the intermediate is not an invariant framework. The top system is, you've got two regular tetrahedra, these are invariant, and they combine, and there were two edges which are folded up onto each other here. So this is the only way to realize this more complex, this particular graph in an invariant way. It's the only way. But you can rotate the two tetrahedra about that common edge, or it's actually a multiple edge. But what's really happening here when you switch an edge is a visual, a realization of a visual, of a sort of perceptual state, a realization as a three-dimensional graph. So what's really happening is you're doing a magician's sleight of hand. So you have this invariant framework, and then you slip it across until the two vertices coincide, and then you come out on the other side and it's become a cube. So this is in fact what is happening with this edge switch and this solution. It's actually necessary to realize the graph in space as a state in order to do this. So states are being realized to affect change. And so let me say, then the only, I think we live in a relational universe, so the only thing that makes sense is how one system relates to another system. And the Necker cube is just lines on a piece of paper, but when they correlate with you or me, then a cube is revealed. Just as when we measure the spin of a particle, the spin is revealed. Up until then, the particle is not in any spin state. So the concept of state is relational. It somehow relates to us and the lines on the paper. So time, thinking about time, how can time come in? And you don't want to impose it from outside. As I was saying, I want to build this model up without supposing any God-given things, and time is one of them, and that becomes very difficult. So the only way out I can see to this is to suppose that a causal sequence is also relational, a state. So whether A becomes before B or B before A is actually part of the state, but it's combined with the spatial state or the geometric state. And so because I can't get a handle on what realization of a state means, I think it means a system changes. And and I'm calling this potential information, but I'm not an expert in information theory. It probably sits with other, I should be using other terminology, but so the lines on the paper contain the potential information of a three-dimensional cube. And a causal sequence is potential information realized in relation to another system. And so with these states and these causal sequences being realized as states in a relational context, then I'd suggest that a sort of a more macroscopic change must come from a sort of, again, because I don't want to have laws imposed from outside, a survival of the fittest principle. This seems to me, so this is a sort of Wheeler's law without law, which involves feedback. So, so I just put up this picture. I challenge you to have one cube going one way and another in those three cubes going the other way. If you make a choice on whether this cube is forward or going inside, that's deterministic for the other cubes. So a sort of one out, all out, so to speak, to account for decoherence. And so as I'm coming close to the end of my time, so these are not so new ideas that a system like the brain manipulates, so it contains subsystems which are referred to executive functions, which manipulate information as distinct from representing that information directly. A particular form of this is attention. which seems to play an especially critical role in determining the contents of consciousness. So I will say that a system has higher order universality if it exploits potential information, so it's realizing that information, to enact its own change. It may also process hard information, and that is the conscious experience with a sort of feedback loop. So again, in works of Gray and Frith and other works, somehow there needs to be a tension between the outside or between two systems for change to occur and for consciousness to emerge as feedback mechanism, error correction. And I just finish with this to illustrate error connection. So this was doing the rounds of social media several years ago. But you read it. I leave you to read it for a few seconds. By the end, it should just boom, fall out without any problem. At the beginning, it's a little bit puzzling. Right, okay. Right, thanks.